Welcome to the module Geometric Topology. This is meant to be a very quick introductory lecture to give you a flavour of a few of the topics that we'll be discussing. So this is really a course about knots, surfaces, and the fundamental group of topological spaces. So I've chosen an example that sort of links knots to surfaces, the so-called Seifert algorithm. And you can find this explained in section 5, I think it is, of the lecture notes. So let me just begin and take you through this example. So the pages are turning rather slowly, so you'll just have to be patient. The next slide, when it comes, is going to show you a number of knot diagrams. These diagrams represent some of the simplest knots, which you can represent with up to seven crossings. There's a hole at the top left, which I guess one could fill in with the so-called unknot, which you can just visualize as a circle. But all the other knots have a number of crossings. That the next one, or the first one after the circle, is the so-called trefoil knot. It's actually a right trefoil knot because there's a left one as well, and they're not equivalent. One is the mirror image of the other, but you can't deform one to the other in space. Then the next one is on the top row is the blue one, is the so-called figure 8 knot, and so on. I actually want to discuss one of the knots in the middle, the so-called, well, it's right in the middle, actually, it's the so-called knot 6-3, it's called, because it can be represented with 6 crossings, the diagram, and it's the third one which has 6 crossings. This one here would be 6-1, this is 6-2, and 6-3 is the one I'm interested in. So I want to tell you about this knot 6-3. Like the one above it, it is actually equivalent to its mirror image, like the figure 8 knot. It can be deformed into its mirror image. Another way of saying that is if you reverse all the crossings in the diagram, you can pass from one knot to the other in space. Now I want to give you a bigger picture of this knot, a slightly different diagram, but it's equivalent to the one in the middle of that page. There's another visualization of the knot 6-3. Now this is really a knot diagram in the sense that I think you can see at each crossing which is the overpass and which is the underpass. So it's really a sort of three-dimensional picture. But you can think of it as a picture in the plane, provided you know at each crossing where two strands meet, which is going over and which is going under. If you know that, then you can obviously construct the knot in space. So that's a picture of the knot 6-3, and we're going to construct a surface out of this knot. And the first thing we have to do is we have to what's called orient the knot. We have to just choose a direction in which we're going around the knot. So if we look at the far left, in fact I've chosen a direction here with the red arrows. You just need one arrow and all the others follow. So I'm really, if you look on the left hand part, I'm going clockwise, but it depends where you look, obviously. So I've just chosen a direction of travel around the knot. What I'm going to do now, and I'll try and show it first of all with a pen, although again there's a delay for some reason, is I'm going to actually split all the crossings by just starting somewhere. I'm going to start on the far left, and I'm just going to follow the arrows. So I'm going to start on the far left. You'll see it in a moment, and then there'll be a better picture. And I'm going to follow the direction of the arrows, and that would take me around parts of the knot, but I have to be careful to make sure I'm following the direction of the arrows. And then if I do that, I get a number of closed curves. You can see them materializing there. I haven't quite finished because I haven't covered. I'm meant to be going sort of parallel to each strand, but then there's also what happens here. I'm going to go like that. That's going to go there. So there's another small closed curve in the top triangle, which is materializing. And similarly, in the bottom, it's sort of a curved triangle, there's going to be another closed curve. So I'm going to end up by getting 3 closed curves by just following the direction of the arrows. And I've no longer got a knot in the sense it's no longer tangled. If you just look at these black curves, they're really 3 unknots, they're called, which you can think of as lying in the plane. They're sometimes called Seifert circles. So here's a slightly better diagram coming up, in which these black curves are shown more boldly. And the number of these curves is important. So in this case, there are 3 closed curves. And in fact, the procedure, I'm doing the so-called Seifert algorithm, doesn't really depend on the crossing data. I didn't need to know what strands were over and under. I end up with these 3 curves. Now I'm going to construct a surface as follows. I'm going to, each of these closed curves will bound a disk. So I can think of having 3 disks, which then I can arrange in space. And I'm going to, but I must remember where the crossings were. And these crossings are going to become twisted strips joining these 3 disks. So let me try and show that on this diagram before I show you the fancy picture. So I've got to try and draw three, let's put this in blue, 3 disks. The patience over the technology. So remember, each crossing, so here's what, this is going to become 1 disk here, this is going to become another disk, and then the big closed curve is going to become a 3rd disk, which contains the first one. And then I have to, for each crossing, what was a crossing, I have to join these disks by sort of twisted bands. You'll see a picture in a moment. So that's what I'm actually drawing now. I'm drawing these crossings, these bands in place of where the crossings were. Of course, there were 6 crossings because the knot was called 6-3. It has 6 crossings. Remember where the crossings were. These crossings become twisted bands. So you'll see a few of them. I'm going to sort of make them bolder here. But there are going to be twisted bands. So you're not seeing the twist here, but you will in a moment. So we join these 3 disks by twisted bands. I'll just wait for those to materialize. And now I'll show you the picture you get when you do that. So I've got to have these 3 disks now arranged in space so that I can see these twisted bands. So that's coming now, and then I'll tell you what we can deduce from that. So here's the picture then. Here you can see the yellow disks, 3 disks, and I've joined them with twisted bands to faithfully represent the diagram on the previous slide. So you can see that you can guess which disk is which, but we have these 3 twisted bands. They're once twisted bands connecting the 3 disks. The reason we twist them is what we want to do is we want to make sure that the boundary of this surface is the knot we started with. So if I didn't twist the bands, I'd get lots of separate unknots. But if you actually follow round the blue boundary of this surface, you'll see it is a single knot. It's just a connected component, this blue curve, if you go all the way around. And it gives you, because of the procedure, it will faithfully be the knot we started with, 6-3. So that's why we twist these things. And the other thing you can say about this surface is that it's 2-sided. It's not like a sort of Mobius band. There are 2 distinct sides. The yellow is on the top of the disks, underneath each disk, I can't show you, but underneath each disk it will be the brown surface. So there's a yellow surface and a brown surface. So because there are two, this is a surface in space, because there are two distinct sides and you can't pass from one to the other, it's what's called an it's an orientable surface. In fact, I've given it an orientation. I should have said the surface is orientable. And then there's something that you can construct called the Euler characteristic. If you've done a course on geometry of surfaces, you'll know about this. But basically, you can divide a surface into small pieces, could be triangles or other pieces, each piece being homeomorphic to a triangle. And then you count up the number of vertices, the number of edges, and the number of regions or faces. And this V minus E minus F is independent of your subdivision, and it's called the Euler number or characteristic. And it's quite easy when you have a picture like that on the right, that all you have to do is, doesn't matter whether the strips are twisted or not, that won't affect the Euler characteristic. But if you actually divide these strips into triangles or rectangles, you can easily see that the Euler characteristic is the number of disks minus the number of strips. So in this case, it's 3 disks, there were these 3 closed curves, or Seifert circles as they're called, and of course the number of strips is the number of crossings, which is 6. So it's 3 minus 6, that's minus 3. That's the Euler characteristic. So we're now close to understanding what this surface is. How can we classify this surface? If we have a number of surfaces that look like this with boundaries that are not, how do we know whether two can be deformed one to the other? That's the problem of classification of surfaces. In this case, we're talking about surfaces with boundary. The classification of surfaces without boundaries, in a sense, simpler, and you may possibly already know that. So what can we say, knowing that the Euler characteristic is minus 3 and the surface is orientable? That actually tells us all we need to know about the surface and the fact that it has one boundary component, namely R0. So we can actually say, we can talk about the genus of an orientable surface, which basically says what we start with to get to the surface we want. And there's this formula that says that for a surface with boundary, the Euler characteristic is 2 minus twice the genus minus the number of boundary components. Here, the boundaries are not, so there's one boundary component, and that will tell you that the genus is 2. Now, a compact surface without boundary with genus 2 is just like the sort of torus with 2 holes or sphere with 2 handles. But we don't quite have that here because we have a boundary. So what this is actually telling us, what the theory is telling us, is that our funny-looking surface on the previous slide is actually homeomorphic too. That's topologically equivalent to this 2-hole torus minus a disk, which could be as small or large as you like, but it has to be topologically a disk. I thought I'd already drawn this on the picture, but it's obviously disappeared. So this thing on the right-hand side, the fact it's truncated, is meant to mean that I've actually removed from the 2-hole torus a small disk on the right-hand side. That will appear in a moment. So I've sort of cut a hole in the torus. There it is. And that's the disk, if you like. So by making this disk bigger, and remember we're just talking about the surface, not the solid inside, you can sort of deform the surface and make the disk much bigger, and eventually you'll get the the surface on the previous page, the so-called Seifert surface, as it's called, on the previous page. So that's an example of sort of passing from knots to surfaces. And we'll be, as I say, we'll be studying that. We'll also be classifying surfaces, first of all, without boundary. If they're orientable, they're just equivalent to a torus with either the sphere or a torus with a number of holes. And then in the last part of the course, we'll be talking about the fundamental group of a surface. So I think I can just finish by talking about the fundamental group, first of all, of the torus with two holes, the genus 2 torus, if you like, as it's called. One writes it T hash T. It's so-called connected sum. It's like making two tori, ordinary tori with one hole, kiss each other, and you get this thing with two holes. So it's sometimes called T sum T, T connected sum T, and D is the disk. So our so-called Seifert surface is this double torus minus the disk. Okay, now I just want to talk finally about the, I'll give you another picture now of the Seifert surface. We saw one picture on the previous slide. Here's a sort of more artistic picture which you get from the previous one by deforming things. And that's coming up now on the left-hand side. So that's topologically, of course it's difficult to tell, but it's topologically the same as the one I showed you before. But it's been smoothed out. So this is an example, as I say, of a Seifert surface. It's related to the knot 6-3. What that means is an orientable surface whose boundary is that knot. And this surface has what's called genus 2. You could find surfaces of higher genus that have that same property, but it's interesting to know what the minimal genus is of a surface that bounds a given knot. And on the right-hand side, I've removed the surface, and there you see the boundary. You can't see the overpasses and underpasses, but you can see the boundary of that surface. And it is, again, represents the knot 6-3. And I've shown you this to sort of make it clear that there are many different diagrams that will represent the same knot in space. We can get away with 6 crossings. Here we have many more, so obviously the diagram's much more complicated. Just a sort of squiggle, but it does represent, if you put in the crossing data, it is a representation of 6-3. But you know, if you rotate the knot in space and take different projections, you'll get different diagrams. Okay, then the final slide is going to tell you very quickly about the so-called fundamental group. This is an introductory lecture, so I'm not going to define it properly. But I want to talk to you about the fundamental group of this genus 2 torus, or torus really means one hole, so I should say the genus 2 surface. The fundamental group is really, it measures the deforming loops in the surface. So you have a number of loops in this surface, the closed curves around. Think of the surface in space. Remember, it's just the surface, not the solid material. So here you can see drawn actually 4 loops, 2 yellow ones, 2 red ones, and they go around the surface. They're meant to go through the same single black point, but I could easily deform them so they go through the same black point. So if you do that, then you can try and sort of move these closed curves, these loops as they're called, around the surface and see whether there's sort of relations between them. And what you discover is that if you take this combination on the third line, you do A, you start with A, and then you do B, and then you go backwards along A, and you go backwards along B, and then you sort of move to, C is A2 and D is B2. Sorry, I meant to update the notation. So you do A, B, go backwards along A, backwards along B, then you go to C, which is A2. You just move along with a curve between the black points. And you go round C, A2 rather, then B2, and then back along A2, backwards along B2. It turns out if you do that, you get a different loop, and you can actually shrink that to the loop that's you just make it smaller and smaller, and it is possible to do that. So you get what's called the identity. These loops form elements in a group. You can multiply them by doing one and then doing the other. It's quite surprising that that's true, but you can, in theory, sort of understand why that's true by fiddling around. So this fundamental group, it's an infinite group. It's generated by these 4 elements, but they do satisfy one relation. Whereas if I were to remove my disk things get much simpler. Removing the disk actually means that there's no relation anymore, because the disk introduces one other loop which you can express in terms of the 4 original ones. So you actually end up with a group, what's called a free group on 4 generators, with no relation, and that's the fundamental group of our Seifert surface. Okay, that's it. That's a very quick introduction, sort of pictures and so on, the sort of things we'll be discussing. This particular topic, the Seifert algorithm that I talked about earlier, is a particularly easy part of the course, and if you're lucky enough to have it in the exam, it usually gives a question which is quite easy to get through. I'll leave it there. You can look at the material on KEATS. As I say, most of what I said in this talk is contained in section 5 of the lecture notes, but you can also look at the introductory section 0 of the lecture notes. And there are also some older introductory lectures which I made about 3 years ago. So I look forward to seeing you hopefully in the first lecture on Monday the 23rd of September at 4 o'clock. Bye-bye.